Welcome to lecture number 3 on signal processing. This is a series of lectures on an introductory level signal processing course, and you can find the rest of the lectures in the playlist. And teaching this course using MATLAB and Python as we develop into the course. And this third lecture, we're going to concentrate on a very important class of signals. These are exponential signals. And this is one of the most important signals for us to think about. It's really gets to the heart of something really important of what we're going to do, which is linear signals. Most of what we're going to consider in this class is thinking about, one way to think about it is linear signal processing. We're going to take signals, think about them in terms of representations of linear signals where we have superposition and we have exponential signals being the foundational way of representing them. Now, why are exponentials sort of foundational? It really gets back to just thinking about measuring, for instance, initially a continuous signal and a linear signal. One way to think about it is a solution of a linear differential equation here, x dot equals ax. So when we think about this linear dynamical system characterized by the matrix A here, the way we solve these dynamical systems or this simple differential equation is to assume an exponential solution. Okay, so what we try is we plug in a solution ansatz of this form, which has, and this x can be a vector, so it'd be some vector v, and you put all the time dependence here in the exponent, e to the lambda t. Now, if you plug this into here, there's only one place you're taking a derivative, which is right there. So x dot, you take the time derivative of this, the lambda comes down, and what you end up with then is an eigenvalue problem. So the eigenvalue problem, when you solve for the eigenvalues and eigenvectors of this matrix A, it gives you some eigenvalues which characterize the time dynamics along with eigenvectors which characterize the direction of this behavior. So the eigenvalue problem is sort of the canonical representation of the solution, and you can add these solutions, these eigenvectors, eigenvalue solutions together to form a sum, which is the linear and superpositioned solution of the system. But again, notice all the solution forms come in the form of an exponential. So this is really critical for us. When we think about linear systems, you should think about exponential solutions are the canonical solutions for that system. So this is what we want to characterize, is these continuous time exponentials initially, then we'll get into discrete time as we go. So here is a generic representation of an exponential in time. Some constant c, e to the alpha t, and by the way, these constants can be in fact have real and imaginary components, and so that's also an important piece of this, is what happens when I have different representations where alpha has a complex representation or c does as well. Mostly we'll concentrate here on alpha in its complex representation. But first, let's start off and just say, what if alpha is real? There's two possibilities. If alpha is real, I could have e to the alpha t, which is exponential growth, which means signals are just growing exponentially. If I also have a real signal with a negative sign in front, e to minus alpha t, this signal just decays. So these are real exponentials. And in some sense, when we think about these in terms of the signal processing context, these are signals we're not going to consider quite very much, because such signals in some sense aren't really interesting to us from a signal processing point of view, because these signals either go to infinity or go to zero. So if I want to process a signal that goes to zero, there's nothing to process. Or if it blows up to infinity, it just becomes infinite, also nothing to process. What we really want are signals that persist over time. In other words, signals that are going to have, instead of a real exponent, that the real part of the exponent is zero, but have an imaginary component. And that's what we want to go after here, is thinking about signal processing. Most of this course is going to be focused on signals of this form, exponentials, but the exponential has complex components. Okay? Or it's purely imaginary. And so those are the exponents we're really interested in. And this gets us right to one of the most important formulas you're going to need for this course, which is the Euler identity. So e to the plus or minus omega t, so if you have purely imaginary exponents, these are nothing more than cosines and sines. Okay, so fundamentally, when you have an exponent with an imaginary component, you're thinking about oscillations, cosines and sines. And this relationship will be used throughout the course. It allows us a way to represent signals, exponential signals, which are solutions to these differential equations, right? That's these linear signals in terms of frequencies. That's what that omega is. That is determining the frequency and period of these signals. And that's exactly what we want to think about when we start representing signals. When I did the first introductory lecture, I talked about all these technologies using different parts of the electromagnetic spectrum or acoustic spectrum for sending information. And so fundamentally, those signals are characterized by their frequency, and this is exactly what this does, is it frames for us a way of characterizing all these signals in terms of some underlying frequency content or bands of frequencies. Okay, so nice thing is imaginary exponentials are periodic or can be periodic, and here's how we're going to look at the period of these things. So I'm going to take a signal e to I omega t, and I want to think about a corresponding signal e that is equivalent, which is e to I omega t plus some capital T. So t would be the period. So if I add the right amount of t, I get back exactly the original signal. You already know this is related to cosines and sines. You already know that cosines and sines have a period of 2 pi. So the idea that this thing happens is not surprising given the fact that this is just cosines and sines in disguise in some sense, or a different alternative representation. So let's talk about computing that periodicity. So we have here e to omega t. I can take my sine rule or exponential rules, and this is e I omega t, e to I omega capital T. And for these two to be equal, this here better be 1. Okay? So that is the periodicity requirement, that e to the I omega t is equal to 1. So what we're looking for is a way to represent this. So this is 1. And so we know that this is cosine omega t plus I sine omega t. And for instance, when this is 2 pi, this is 1. So take this and you can say, oh, this is equal to cosine of 2 pi, which is 1, plus I sine of 2 pi, which is 0. So it's exactly 1, okay? So this relationship holds. So you can make these two equivalent by saying omega t is equal to 2 pi. And that gives you then the period here. Here is the period. It's 2 pi over omega. Okay, so that's one way of starting thinking about calculating this periodicity. And one of the things that we're going to already talk about later is that this, in fact, doesn't have to be 2 pi. It could be any 2 pi n, right? So I can have n being anything here, and I still can get a periodicity requirement. And so there's going to be this concept of what's called a fundamental period, and then just periodicity in general. Okay, so what we're looking for then is the smallest t for which the periodicity holds, and that is going to be our fundamental period in this system. So we're going to come back to that in a moment, but more generically, we're going to talk about it in relationship to essentially this idea of general sinusoids. We know that these exponentials decompose themselves into sines and cosines, so let's just talk about a generic sinusoid, and here it is. I can take a cosine. It's characterized by some amplitude A, some frequency omega, and this is going to be a phase offset. So it turns out if, for instance, this phase offset is pi over 2, this cosine turns into a sine. So I can generically just stick with a cosine, and buried within it is a sine because the sine is just a shift by a certain phase. Okay? So this is a very generic structure characterized by 3 important parameters: the amplitude, the frequency, and the phase. Now the amplitude is very important in terms of calculating the amount of energy delivered in a signal. The bigger A is, the more energy is delivered in this signal here. The frequency, omega, characterized at the period of the system or the frequency of the system, and as we've talked about all these technologies that exist at different bandwidths, this is going to be a way of characterizing whether you're infrared, ultraviolet, visible, wherever you are in the electromagnetic spectrum, it's typically characterized by omega. And the phase just tells you a little bit about essentially where the center of time is, in one way to think about it. So you can do this all with a cosine. You don't need sines even, or you could have done it all with sines, because sines and cosines are simply related by a phase shift. So this is a very general way of formulating a signal that is an exponential with purely imaginary part. That's the formulation right here. This is an equivalent way to represent the signal, and this is a real signal. So whenever you take an exponential with imaginary part, it's a complex field, and what you'd really be reading off is the real part. Here you've already got everything in terms of real part. In signals and circuits, this is typically thought about as the phasor notation of the system. So here it is. Here's the general sinusoid that we have here, and you can see all the characterizations that we have here. You have your basic amplitude of that signal. You have your basic phase shift of that signal. There it is. And then you have your basic underlying period that you would have with this thing, okay, which goes to here. Okay, so these are the different ways of characterizing a signal, parameterized by 3 numbers. And so just keep that in mind. Whenever you think about a signal, you have to tell me about its frequency, you have to tell me about its amplitude and its phase. That's the way to kind of uniquely characterize that signal in terms of very important quantities, such as what's the energy content, what's its bandwidth. These are the kind of things that you would use to give me that kind of information. All right, so let's talk about this more and making the connection more clearly between the exponential and sinusoids. Okay, so in exponential form, I can just write this cosine directly out in this form here, which is essentially, I can take the cosine. Cosine is e to the I omega t plus e to minus I omega t over 2. So but now I have not just omega t, I have omega t plus phi. So this is kind of what you get in terms of that representation. So I took a real representation and wrote it as complex exponentials. That's what we started with, right? The solution to that linear equation was e to the I omega t. So these are alternative formulations, and there's great advantage to writing it sometimes like this, and there's great advantage sometimes to writing it sometimes like that. So we will use them to our advantage whenever we can, right? We want the simplest representation to solve problems that we have available to us, and so that's going to allow us to do that. All right, so alternatively, you can say, well, this a cosine omega t plus phi is just the real part of this complex signal, and sine is just the imaginary part of this complex signal. So these are just all alternatives for us. Your goal in signal processing is to just use the one representation that is the sort of, in some sense, mathematically easiest for doing some kind of signal processing operations. Okay, let's talk about the power and energy, because the power and energy delivered by these exponential signals very much matter. And so we can think about the energy delivered over a period is just simply integrate over a period t. You take e to the I omega t, take the absolute value of this, and the absolute value of this is just 1. Okay? And you integrate then 1 dt, and then your energy is just the period. Notice that I don't have an amplitude in front of this. If I had an amplitude a e to the I omega t, I'd have an a squared here, an a here in front, it's a times t. Okay. But you could see that the energy is related to the period. So as I go more and more periods, the energy it grows. In fact, if I integrate the total energy in a periodic signal is infinity, because I would integrate over all of periods from negative infinity to infinity, and that would be basically integrating 1 from negative infinity to infinity. The power itself is, again, now you take that energy over the period, divide by the total time band t, and in this case, if the energy is t, divide by t, it's 1. Okay, so that's the average power in a period. So you can compute these things for these exponentials, which are going to be probably the most important class of signals we consider throughout this course is these sines and cosines, or these exponential representations, which also are going to get us later in this course to talking directly about the Fourier transform, because the Fourier transform is all about taking signals and representing them in terms of cosines and sines, or these exponential representations. And it's probably the most important transform that's ever been developed in human history at this point, right? It's taking a signal. This representation is one of the most widely used representations that we have in terms of a canonical transform that applies almost across every discipline in the sciences. And really, at the end of the day, the Fourier transform is just simply saying, if I have a signal, I want to represent it in terms of frequency content and the energy at each frequency. And so it's a really nice representation that's very generic and easily used across disciplines. Very nice interpretable results. All right, let's talk about harmonics then, because we've already talked about the fact that these signals are periodic, but then one of the calculations we did right at the beginning is we said, hey, to calculate that period, I say e to the I2 pi was 1 to calculate the period, but really e to the 2 pi n is 1. So this gives us a much broader view of computing a period, right? Because you could have this condition hold, and so there's lots of periods t that can work, right? For n goes 0, plus or minus 1, plus or minus 2, and so forth. So there's different ways to pick the period of a signal, and oftentimes we're interested in the fundamental frequency, but let me just show you here. You're already familiar with this. Take this signal here. Here it's one oscillation. So over this time bin here, and this is a bin of pi, right? So this signal takes one oscillation. That's its period. However, cosine t, notice that it oscillates twice. So this is still a period for this signal, but really the period could be half of that. But that does not make this, but still pi is still periodic for this thing. Same thing with the other signals up here. These are all periodic, so now you get 3 periods in there and then 4 periods on there and so forth. So what you have here in this interval 0 to pi, it's a period for all of these signals. However, only for this one is it a fundamental. This is the fundamental period. So this is how we define a fundamental period. It is the lowest value of capital T that allows us to have periodic signals. Okay, so that's how we think about this idea of a concept of fundamental period. All right. What happens if we have real parts of a signal plus these imaginary components? So the real parts usually are exponentially growing or decaying, and the imaginary parts are oscillating. So more generically, here's how you would represent signals. This is if you have a real part that's positive, so the signal does exponentially grow, but it's oscillating at the same time. And same thing here for if you have a negative real part of the signal, it's decaying to 0 and oscillating. It does so. Again, we won't be considering these signals as much because these signals either go to infinity or go to 0, and what we're really looking for is solutions and signals that persist over time, which means we're really looking for the real part of the signal to be 0 so that we don't have exponential growth or exponential decay. So that's what we're considering in most of what we're going to be doing. So let's move on now to talk about discrete time signals. Okay, so in discrete time, if you remember, this is the canonical representation. X of n is going to be some constant c, alpha to some n. So this is a way of representing a discrete time signal. Now n here, this is interesting because think about this alpha. If alpha is greater than 1, or its absolute value is greater than 1, then I take some number and I keep multiplying by itself over and over again. If it's bigger than 1, it's going to go to infinity. If it's less than 1, it's going to 0. And then this very interesting case where if alpha is, in fact, the absolute value is 1, it will be periodic. So we're already going to start setting ourselves up for this by rewriting that signal in terms of an exponential in the discrete time. So we could always write this as e to the beta n, where here's a relationship between alpha and beta. Okay, these are just two interpretations of that same signal, but this one here is a little bit more flexible for us in terms of thinking about periodic signals, as you'll see, because if this thing here already has the exponential form where if beta is purely imaginary, this is going to be, again, cosines and sines, which are the signals that we're most interested in. So let's take some view of this. So let's just go ahead and take some signal x of n, c alpha n, and let's just construct some cases. So here, if alpha is greater than 1, as I already mentioned, if alpha is greater than 1, this thing is just going to blow up. Okay, so we're going to take alpha to be real and bigger than 1. So for instance, if alpha is 2, you keep multiplying by itself, so you get 2, 4, 8, so forth. And so this thing is just going to grow exponentially. Okay. However, it's between 0 and 1, then you have a number like, for instance, take a value like 1/2, and you multiply 1/2 by 1/2, you get 1/4, and then you multiply by half again, you get 1/8. And so now it's going to exponentially decay. That's for alpha being between 0 and 1. If you have alpha between 0 and -1, now it's not only going to decay, but it's going to alternate signs. So every time you multiply, you keep changing the sign of the signal, and that's why you see this oscillation essentially, or the sign change as you decay. And if alpha is negative, less than -1, now you get exponential growth with an alternating sign. So these are like 4 canonical signals that you would get by having this form of solution. And notice what I've avoided here is the absolute, or alpha being 1 exactly. And alpha being 1 is actually the case we're most interested in, because these, either they go to 0 or they blow up. So very much like the continuous signals where, you know, the real part's positive or negative, things go to infinity or 0. We're not as interested in this. We're interested in signals that persist over time. Okay? So we're going to not do much work with these. We're going to be more looking at these kind of signals here. And this is why we wanted to write this in exponential form, is because once we have it in this form, e to the I omega n, these exponentials in this form for the discrete case, we know that that is essentially equivalent to this kind of formulation here, a cosine omega n plus phi. So these are sort of in some sense related to each other because they're looking at exponentials. And in fact, down here, you can see that essentially this form of this, where alpha, you know, is the absolute of alpha is exactly 1. In other words, you're sitting on a spot where you're going to always have periodic solutions, which we can represent in either of these two forms. All right, so here's a simple example. Here is the function cosine 2 pi n over 12. And what we're going to do here is just simply change this to cosine 8 pi n over 31, cosine number is 8. And you can see here's these different signals that we get that clearly are bounded between 1 and -1 because they are cosines. And also as we change the frequencies, you can get different oscillation patterns in these. And what we want to start to understand, what is the difference between what we see in the discrete signal and what we see in the continuous signal? And there is one very big difference between these, and that's going to be something that we have to characterize. So as we start to play around with working between discrete and continuous signals, we want to start thinking a little bit about what are the big differences there. So let's talk about first periodicity. So remember, we have e to the I omega n, but now we can add any 2 pi to this, and I get back the same signal. So this is kind of exactly what we started working with when we were looking at the periodicity of our signals previously. We were looking at this thing here. As long as this thing here is, well, it is, in fact, this is 1. Signals at omega are identical to signals at omega plus 2 pi n. So this is a really important result for the discrete case, because what it's telling us is all I need to work with is some band of frequencies, whether it's 0 to 2 omega, or 0 to 2 pi, or negative pi to pi. I can pick one of these two bins. All other signals outside of that frequency bin, or I can come back, are represented in terms of this initial bin, the fundamental bin, whether it's this or this. Okay, because they're identical. Here it is. That's the result. That's what this tells you. Okay, this is very different than continuous signals. So as I start increasing the frequency, right, you get more and more oscillations. So for instance, consider cosine t, cosine 2t, cosine 3t, and so forth, right? Higher and higher oscillations. And what we're going to show here is that as you continue to increase the frequency, in fact, your signals come back to their original representations. They don't get higher and higher frequencies. They actually kind of wrap around and have a nice representation in terms of this base set of frequencies between 0 and 2 pi. So let's calculate the fundamental period of this. Same kind of calculation. You have e to the I omega n plus n. So let's say n is going to be our number of shifts that we have, and we want to ask how many do I do to get back to the original signal. So period n is there. So I have to have this condition here. I omega n is equal to 1. And so of course we know that if this is 2 pi, then we'll have our periodicity condition. So there it is. And so we have a fundamental period when n is equal to n over 2 pi over omega. Now notice we have two integers here. So before in the continuous case, we just had 2 pi over omega, and now what we have is n 2 pi over omega. So we have both the integer n, which is from our our discrete model, e to the I omega n, that's that n, and now we have capital N, which is the periodicity of this thing, which is also an integer. So this is a really important calculation, which gives us our fundamental period. And so let's start doing an experiment here. And this is what I want to kind of highlight to you. So as we ramp up the frequency, essentially, that's what we're doing here. So this is a cosine of 0n, and we're just going to start ramping up pi over 8, pi over 4. And we're going to start ramping this thing up. Notice what happens. We start to see this oscillation. It gets faster, but then as we keep ramping it up, we eventually get back to the original signal. And this is what I was talking about. So once you go through this 2 pi bin, if you just keep ramping up frequency in this model, you get back to where you started. This is very different than if you take a cosine, you start ramping up the frequency, it just gets faster and faster oscillations. Here, you ramp up the signal, it starts getting fast, then it comes back down to its original base. Okay? So in other words, as you do this, you get sort of a periodicity also as you increase the frequency. So in fact, if you do this, notice that as you increase, this guy becomes this, this is this, this is this. So here you go from here, you ramp it up, you get to here, and now you start repeating the signals you had before. So this is an important difference between continuous and discrete. It's really important that you understand this difference because it will come up quite a bit as we process signals. And again, just compare this to continuous case. As you start ramping up the frequencies, you just get more and more and more oscillations. It's not like as if you ramp up the frequency, you get back to this, right? You just keep adding oscillations to infinity. Here, what this is almost saying, the discrete case starts from here and it comes back to here if you keep ramping this up. That's exactly what this shows. So we just want to have that understanding, which tells us then all I have to work with is a fundamental bin of from 0 to 2 pi or negative pi to pi. I can pick whichever I want and work with that bin, and then I get all possible signals out of that bin. All right, just as a summary of this difference between the continuous and discrete case, I made a little chart here. So for the continuous case, distinct signals for distinct values of omega naught. So, okay, so you just keep increasing omega naught and you always get new signals. So, okay, omega naught is 2 versus 4. These are two different frequencies, right? Cosine omega t, cosine 4 omega t. However, for the discrete case, you get identical signals if you just ramp this up by 2 pi. So once you keep ramping this up and you get 2 pi higher values of omega naught, it's the same signal. Exactly the same signal, okay? So the periodicity conditions, for any choice of omega t, you get a period. However, here you have to have these integer relationships between the period and the n itself of your model, okay? The fundamental frequency you can find is omega naught, and you can find some fundamental period, which is defined here, and then your fundamental frequency here is omega naught over m, and then you get a relationship to a fundamental period. So kind of these important distinctions between the two. We will work alternatively between discrete time and continuous time throughout the course. And you can see this is one of the big differences that we have in the representation is this way of characterizing frequencies. What are the possible frequencies that you can even have? Clearly with discrete, you have a band of frequencies that keep repeating itself. So you live in a 0 to 2 pi domain period, frequency band in the discrete case, whereas in the continuous case, you can keep ramping your frequencies up and get any frequency you want just by simply increasing that, and then it changes the period as well. So exponential signals, specifically complex exponentials, which are cosines and sines, are going to be one of the most important things we consider in this class. It's going to be related to the Fourier transform. And maybe one way to characterize this whole class, it's all about Fourier analysis or Fourier series, because almost all the signals of interest to us are going to be cosines and sines. They persist for all of time, and we're going to do a lot of signal processing around these signals that have underlying characteristic frequencies. And so we're going to have this representation both in the time domain and the frequency domain, and we're going to use them jointly together to do all of our signal processing operations.